So let us move on. Now that we have set the stage, let's get into the some more specific terminologies and usage, because we completed the interactions, right. So we understood the different types of interactions, different types of ionizing radiations, what is of interest, and what is of interest to a X-ray tube from a generation point of view, what is of interest from an imaging point of view, right, what physics, what phenomena are involved, what types of interactions are involved, all that has been completed. So if we have to progress further, because our objective is imaging system, understanding the physics and then engineering it so that we can capture an image of the unknown distribution, right, that is our big picture. So that means we need to march forward with the understanding of the physics. How do we capture, how do we engineer that, right. So before we can engineer, I think you need to have some equations. So there is this phenomenon, there is this physics, there is this intuition. Somehow we need to have a common language so that we can put them in a mathematical form and then exploit it to get the imaging system model and the image, right. So having said that, let's move on. Now we want to talk about the interactions that we just talked about, some interactions, right, electromagnetic radiation interacting with material. So now let's introduce some terminologies to how to describe them more quantitatively, how to model them more quantitatively. Okay, one of the important interactions that we want to capture, right, we didn't use this term so far, we probably used it in introduction lightly, attenuation of electromagnetic radiation. In some sense, if you recall, I said, oh, you shoot and you shoot X-ray energy, something comes out. So through transmission is what we will discuss. So when you do that, the electromagnetic radiation is interacting with body, and we talked about important interactions of this electromagnetic radiation. One is photoelectric, the other is Compton. What happens in photoelectric is absorbed, we said, that means there is loss of energy. So more correct terminology to describe it is the attenuation. So you send some energy is reduced, you send some photons, number of photons reduced, it depends, we will have to be little more clear on that, but the idea is you send something in, something to do with X-ray in, and that gets reduced when it comes out, because it is interacting with it is losing out to the tissue or the material or the medium that it is interacting. So we now talk about attenuation of electromagnetic radiation. So that means we need to first and foremost, okay, I am sending X-rays, it is interacting and something is getting lost, and that is what it is getting lost, or it is getting reduced or attenuated because of the interaction with the material. So the material is able to make something happen here. Okay, that means we need to talk about how do we describe that. So we can talk in terms of X-ray, what am I sending in? Loosely we said X-ray, but what more specifically of X-ray? So we need to talk about how do we characterize, how do we quantify, how do we describe objectively, what do we mean by beam strength. Okay, if we can send a beam strength, right, that is getting reduced or because of attenuation due to the material specific property, right, that is what we want to, and then it comes out. Based on what comes out, we know what we sent in, we know what comes out, we need to see the attenuation is the property, right, that is the unknown of the body that we are trying to estimate. How much is attenuation, where it is, right, distribution. X-ray beam. So the easiest way to do it is what? We talked about X-ray energy as photons, packets of energy, photons, right. So easiest thing is I send so many photons in, right, of X-ray energy in that energy range. I send so many photons, out comes so many photons. So it is easier to talk about beam strength in terms of number of photons that are going through, right. So that is the simplest measure, number of photons, that's good. But then we should contextualize little bit further, because you are sending, I am interested in imaging this body, for example. So there is a target medium, right. So I am sending it, So I am not interested whether this X-ray is going and reaching the side of the room. I am interested in the X-ray that is going to interact with the body, right? So X-rays are going, and then I have a volume, let's take a surface, right, that is perpendicular to the propagation. So my interest is how much of the photons are crossing per area or something to do with the cross section, right. If I can normalize that, that will be the, even though number of photon itself is good enough, number of photons per cross section is probably lot more meaningful, right. So n is a burst, area of spread is also important, right, whether I am sending how many over this surface area, right, it has go through and come to the other side. So the cross section perpendicular to the direction of the n photons that are going, right, that is important. So we can normalize that, we call that as photon fluence. So there will be several definitions, right, that we will incorporate, now describe here. If you just read at it, try to by heart, it will be confusing, okay. So just go with the flow that I try to organize here, talk through loud, explain the concept loudly so that it gets you understand, you won't get confused, you understand the flow of how these are built up. Fluence, photon fluence, photons, fluence, flow, right. So number of photons traveling across a cross section normalized, right. So n over a is your photon fluence. Carefully look at, I mean, these symbols, all those things will complicate life, right. I mean, usually that's the confusing part. So don't worry about all that. Concept, photon fluence is photons per area, perpendicular, the cross section perpendicular to the flow of the photons. Okay, that is good, but then we should also be interested, if I send some photon, out comes the photon, I have to detect it. I cannot wait indefinitely, right. I have to send the next burst of photon, next detect that. So in some sense, yeah, photon per cross section is good, but then the rate at which it is coming, that is also important. So that is photon fluence rate. What is flow rate? Is a temporal, it talks about the normalizing with the time. So this is the fluence per unit time, right. So n by a per delta t, that is the fluence rate, right. Okay, good. So fluence is fine, fluence rate is fine. So this is good enough, but then one may argue, look, we talked about in X-rays, we were talking about energies, right. In fact, if you really paid attention to probably 1 or 2 sentences I would have made in the introduction is, oh, in PET we end up counting the number of, the radioactive number of photons, whereas in X-ray based modality of radiography or X-ray CT, we are more interested in the energy part, right. So you might just wonder, oh, he talked about n, number of photons, beam strength in terms of number of photons, but reality, even just before this we were worried about the energy levels. So would that be a better measure of describing this X-ray beam strength, right. So yes, you can do that, you will end up doing that, at least for the X-ray part. You are not really interested in number of photons per se, you are interested in the energy that is flowing, X-ray energy that is flowing through. For simplicity, we will say if there is only one energy that is coming out, so the n photons that are coming out are all coming out with the same energy. What is that energy? E is equal to h mu, right. So that means I could write, instead of n by a, if each photon has h mu energy, then I can write the energy fluence, right. So the energy fluence is n times each one has h mu, n times each photon has h mu, right. So this is your energy fluence. Naturally extending this analogous here, if you have photon fluence rate, you can have energy fluence rate, which is going to be per time, right. So n h mu by n a delta t, n h mu by A delta t. Wow, probably you wouldn't have heard, right, energy fluence rate. What is it saying? It's talking about the energy that is flowing across a cross section A, right, unit cross section across time delta t, X-ray energy. So, but you wouldn't have probably used this sophisticated term. Most commonly you would have heard, or you be more familiar with the usage called intensity, right, intensity of X-ray. That is what you would have probably, if you had a chance to brush through, or if you know, this is what you will find. Intensity is nothing but energy fluence rate. So, do not get confused, right. So, that is why I said a lot of terms, but then it is very intuitive, very straightforward, very common sense extension of each of the concept. So, intensity is this guy. So, we will write it, intensity is I is equal to energy times, of course, this variable did not come out correctly in my fonts here. This is supposed to be, right, n h mu is the, right, n h mu is the energy per photon, n by A delta t is this guy, fluence rate. So, intensity is nothing but energy of the photon and the fluence of that photon, right. So, number of photons at that energy level that are crossing area A, right, at temporal delta t, some rate. Okay, so this is what you will. Okay, so far so good. So, we know about intensity, but don't you think we already made some simplification? What could be that simplification? If you are observant, you will say, oh, this is fine, life can be little more complicated. Why didn't we talk about energy of X-ray coming out from X-ray tube? That is what is going to be given to the body, right. What is the nature of X-ray energies, right? What is the interaction that produces X-ray in X-ray tube? Is there something that we need to clarify further, right? So, here polyenergetic sources. What do we mean by polyenergetic sources? Poly is many, energetic means so different energy. So, sources that are sending different energy. We talked about this just in the previous lecture. We talked about X-ray tube generating the X-ray, this X-ray, right, Bremsstrahlung, remember. So, there were discrete characteristic X-rays, but then predominantly the X-rays generated in the X-ray tube is due to the Bremsstrahlung interaction, where you saw the continuous. So, there was energy levels, different energy levels that were there, right. It was going up and the hill shape, right, it was going up and then coming down. Yeah. So, what we covered just now is for photon with one energy level, but what I am sending is going to be having different energies, right, because different photons are coming, there is a distribution, it is all statistical, right, there is going to be distribution. So, how do I kind of describe that, how do I capture that, right, when you know the polyenergetic is the source. So, n photon with each having the same energy is fine. How do I write about, or how do I capture polyenergetic sources? Straightforward. So, now we need to just recall what we meant by that, right, Bremsstrahlung. So, literally you have to look at this definition and recall that plot that you saw and internalize the concept there as to how do you interpret that plot. What was that plot? That plot said there was an energy axis, number of photons, right, that was the relative intensity that was coming out and the energy that it was operated, right, that was the hill shape. So, Bremsstrahlung means it is going to give out, each burst is going to have different energies. At each energy you are going to have some number of photons, right. So, you have a distribution of spectral lines, that is you have energy in one axis, number of photons in another axis, then you are going to have a distribution, several energy. At each energy level there is some n number of photons that are coming out. See, that is how to view this, right. So, you can talk about this as spectral lines, remember. So, we are talking about X-ray spectrum S of E. If it is only one energy, no problem. If you have multiple energies, then I have what is called as a X-ray spectrum. That means I have S of spectrum of energy. At each energy level, I may have some n number of photons. So, at the highest level, remember, just to complete the recollection with what we did already. At the highest, in the Bremsstrahl lung, when the thing is annihilated, right, you have complete loss of it. So, the highest energy does not come out. That, I mean, at least relatively speaking, we said that if it was 120 kilovolts applied voltage, you will get 120 kilo electron volt energy, and if you look at that plot, it was almost 0. You did not really have any energy photons coming with 120 kilo electron volt, because we said that is a rare interaction, complete annihilation. More number of photons come, at a range that is less than, the peak of the hill is much less than your highest voltage or the highest energy that you are sending. Just recall that. So, you could expect that means X-ray spectrum is different energy levels, you have different n number of photons. There is going to be a distribution of photon energies. So, number of photons with energy E per unit area per unit time. So, we can define it this way, right. So, we are interested in number of photons with energy E per unit area per unit time, correct. So, we talked about number of photons in the previous slide. We talked about number of photons per unit area per unit time, each having the same energy. So, here we are just telling that, oh, this has energy E, but the burst may have several energies. At each energy level you may have different n, okay. So, in some sense, photon fluence rate, if it is a spectrum that is going in, right, if it is a spectrum that we are describing, it has to be integration of all. So, spectrum of S E dashed d E dash. So, this is your dummy variable. So, that means what is this saying? Fluence rate, number of photons per unit area per unit time. I am given the energy spectrum. What does that say? Number of photons at each energy. So, total number of photons that are going in is nothing but sum of all the photons at different energy levels. That is what the sum is, what is your integral. So, your phi is the total number of photons with each. So, each energy level, whatever is that spectrum number n number of photons at that level, you sum the total photons that are going in, right. So, that is what is your fluence rate. So, what is the other thing of interest? Intensity. Okay, this is the number of photons. What will be the energy? Well, when we had only one energy, we equated n E is equal to h mu, and so we talked about total n h mu. Here you have n1 with energy 1, n2 photons at energy 2, right, n3 photons at energy 3. So, you have a distribution. So, what will be the energy? Guess. Without knowing much, we could already guess that. Why don't you multiply the corresponding number of photons with corresponding. So, if I have n1 photons with energy E1, then the energy is n1 E1 plus n2 E2 plus n3 E3, right. I could stretch your imagination, so it is straightforward extension, right. So, intensity of polyenergetic source is therefore number of photons at each energy level into that energy level, sum of all of them, which is your integral here, each energy source, right, E dashed into S of E dash. S of E dash has number of photons, S of E dash at each energy level, the spectra has S of E is n number of photons at that particular energy level. So, E dashed is the energy of energy level, number of photons at that energy level E dashed. S of E dash is number of photons having E dashed energy. So E dashed into number of photons having E dashed, you do that for all energies, right. So since we talked about that as a continuous space, right, when you saw the Bremsstrahlung, it was a continuous. So dE is that small increment that you are doing. So your intensity is this guy. Very good. So now what we have done is, we wanted to cover attenuation, right. So now what we have done is, before going to attenuation, defining attenuation as something is lost, we have actually quantified what is going in. We can actually talk, we can talk in terms of X-ray beam strength. You either write it in terms of photon, or you write it in terms of energy, you write it in terms of monoenergetic, or you write it in terms of polyenergetic. We know how to describe how much of what you are sending in. Next, what is the logic? Oh, next that means we need to be able to define how much is coming out and relate what is coming out to what is going in terms of the loss that is happening, or in terms of the material properties that is contributing to this loss, or what we call as attenuation, right. So narrow beam, monoenergetic, photon. So let us take simple cases at a time. So what I mean is, now we need to tie down what you sent in, what comes out in terms of the medium, right. So we will take a simple case first before going into complicated human body with the 3D volume, right, which is what we will do. Make life simple. We will just take a slab, right, of a particular thickness delta x, small thickness delta x. On one side I am sending n photon. So I am sending n photon, I am taking a small slab, out comes, I have a detector to capture what is coming through. Clear? So what do you think is going to happen? You see some interaction. So the photon, electromagnetic radiation, is going to interact with this material, right. That is what we talked about. Two effects. One is photoelectric effect. So there is going to be absorption, and then characteristic emission, all that energy is reduced, and then it comes out of the slab, right. The other thing is, it is interacting scattered across. So what you will capture the detector is anything that is coming through and hitting the detector, that you will capture. So what you are going to capture is going to be less than what you sent. In terms of photons, if you see number of photons that you send, if it is n, you are not going to capture all n because of this interaction. There is a loss because of this interaction, because of the material. Of course, there is also loss because what is exiting through the slab is not hitting the detector, the scattering part. Whatever said and done, we will tease out that part later, but at least we are clear what you detect is going to be less than what you sent in, and that is due to this loss, due to the medium interaction, right. Okay, so that is fine. What do we mean by monoenergetic? Photons is straightforward, right. Simple cases, just deal with photon having only h mu, right. That all the photons that are coming have the same energy h mu. So that is monoenergetic. What do you mean by narrow beam? So it has to have a context, right. What is narrow? Narrow with respect to what? Why is it narrow? Oh, we are sending here x, right. The photons are coming, the cross section area that we talked about, right. So it's coming, the detector is going to capture only this cross section, right. Only this cross section the detector is going to capture. So narrow means the beam that is coming in relation to the size of the detector. Okay. So here the detector is small, so I can only capture this one. So it is narrow because of this condition, because of the size of the detector. Okay. So narrow beam means the width of the beam is of the size of your detector. Okay. So now what we need to do, having said all what we have said, it's just now question of putting all the concept together. So I know how to describe what is going in, I know how to describe the interaction, or at least I know what the interactions are, I have to model, and then I know something is going to come out, I know that it is going to be less than what I sent in. So what do we do? Okay, so let's do a simple thought experiment. So attenuation is just loss. Okay, just keep that level of simplistic interpretation. Attenuation is the loss, reduction. Okay, so let's do this thought experiment. What happens if I don't have this slab? Right, and assume the medium that is there, right, separated between these two is vacuum. I mean, even if it is, no, there is not much to interact. So the medium is absent. What is going to happen? Oh, what you sent is going to come out. There is no loss. Right. So if I put the medium, I know there is a loss. So instead of I put in n, I have delta x is the thickness through which it is traveling, and there is a reduction. What would happen, right, if I double this delta x? If I have 2 delta x, what do you think is going to happen? Oh, if that is the case, I will get even less, right? In fact, if I double this, I'll probably expect it to be halved, right? Because if there is a delta x, there is a small loss. If I double that, 2 delta x, probably the loss will also double, right? Or I have the same delta x, but instead of sending n photons, I sent 2n photons. What do you think is going to happen? Well, the number of photons that are lost, now you will have 2 times, because the percentage is same, right? The medium is same. Oh, that means 2 times number of photons will be lost. So in other words, you can sense that the loss, the number of photons that you are losing, right, is proportional to, directly proportional to this delta x or what you start with, right. So what you know is n dashed is less than n is what you are sending in, n dash is what you are receiving. You know n dash is less than n. So if you do this thought experiment, then you can write n is your number of photons that are lost, right? N is number of photons that are lost. You can, number of photons that are lost is proportional to delta x, proportional to capital N, right. So this proportionality constant mu is your linear attenuation constant. So number of photons lost is directly proportional to n and delta x. So you use this proportionality constant, linear attenuation coefficient, right. This is to make it equal. So photons lost is equal to mu n delta x. So this has to do with the material property, right. So you can write that as mu is equal to n by n, which is your number of photons lost divided by total number of photons that was sent in, over the length delta x. Clear? So this is a material property. Okay. So in this case, we have only one material with certain value mu. So we will just finish this part and then add to make it a little more realistic. Okay. So now we considered monoenergetic photons, narrow beam, there was only one material, delta x thickness. So you can relate from the input output based on the loss, based on the attenuation, right. We as attenuation as in there is a loss, right, n dash less than n, we can write our mu. Okay. So let us try to put that together. So delta n is n dash minus n, what is n dashed minus n? N dashed is the output, number of photons that are coming hitting the detector. N is the number of photons that went in. So, n delta n is number of photons that are lost, is n dashed minus n, which is output is less than input, right. Therefore, it has to be minus n, and we know that minus n, we know this n is mu n delta x. So, delta n is the number of photons that are lost is equal to mu n delta x. So, we can quickly look at this and say, oh, there are these delta quantities, right. How can I when what happens when this material delta x goes to 0? We never said, we just said delta x. What happens if this delta x approaches 0, right? Clear? What do you get? You can get d differential, right? So, you can write d by dn by n equal to mu dx, or you can solve this, use the boundary condition and say, oh, at x is equal to 0, which is basically where there is no material, whatever you send you get some n naught. N naught is your, without any obstruction, whatever n you send, estimate of that is your n naught, right. So, boundary condition if you will, right. So, n is equal to, if you solve this using this boundary condition, you can write n is equal to n naught e power minus mu delta x. Very powerful. So, what you are saying is your n naught, whatever you are measuring the photon n, after it has travelled a delta x through a medium with mu, there is a exponential decay, exponential loss, right, e power minus mu del x. So, n naught, when n naught is sent in through a material delta x having a mu coefficient, right, the attenuation constant, if that is the case, what comes out is equal to n naught e power. So, it is decayed exponentially. Okay. Fantastic. This is the fundamental photon attenuation law, very powerful. This is what we will exploit time and again in not only the X-ray part, it is after all photon is decaying with the material interaction. So, right, so same idea can be used for our SPECT also. So, projection radiography, CT, positron emission tomography, SPECT, all of those we will use this concept. Okay. So, the idea is you get the big picture view. Big picture view is, if I can know how much I send in and if I can detect what is coming out, based on that input and output, my job is to get the material property mu, right, clear. So, of course, there is some delta x that also we need to account for, but the idea is this is the inherent property that we are trying to capture. Okay. So, how we do that with spatially, volume, all that will become interesting, but all of that captures starts from here. Okay. So, simplest cases, like we said, n is fine. For monoenergetic case, very straightforward. I can write it as intensity is equal to I naught, n is equal to n times, remember each n has h mu energy. So, we can directly, monoenergetic case is straightforward, I is equal to I naught e power minus mu delta x. I send some intensity through this material having a property mu and length of delta x over which it is coming out. So, then the intensity that comes out will be reduced or exponentially decayed of what went in. Okay, that is how you read it. Good. So, that is your monoenergetic case. Once important concept or important metric that usually you capture from here is half value layer. Why is that important? See, here you talk about attenuation, you send something, something comes out. This half is always important for us, right? Full width at half maximum, minus 3 dB, half power point, half amplitude point. This half is always a is something, right? Something is reducing. We would like to know for whatever reason 50% is some salient number, right? So the idea is, okay, what is the, for a given material, what is the thickness delta x when it will be 50% attenuated? That is something that people would like to know. Okay, so that is called as half value layer, which is the thickness. So if I give you a material, right, delta x, I give you a material of lead, I give you a material of soft tissue, I give a material of slab, right, of bone, I give a slab of titanium, I give a slab of whatever, aluminum. Each of the material has its own mu. If I say their job, if I send energy n, right, n photons, out comes n by 2 photons. If that is the requirement, do you think the thickness of each of the material is going to be same? Intuitively not, right? Because each one is, some are more attenuating, some are less attenuating. If it is less attenuating, it will be probably thick, because you have to go through, if mu is less, delta x has to be more, so as to keep I by I naught a constant at 50% in this case, right. So if it is more attenuating, right, mu is high, then delta x has to be small, right. The thinness or thickness varies as the material property, and therefore this half value layer thickness is a important concept. So it's straightforward, right. So that means you apply this definition, your output is 50% of your input. I have some mu, I will call that thickness delta x as my half value layer thickness, right. So n by n naught is half, which is equal to e power minus mu delta x, but the delta x which reduces to 50%, right, the input, that thickness I am calling it as not delta x, I am calling it as HVL, half value layer thickness. So if you just do some manipulation, right, you have E, you have half, take logarithm, natural logarithm, right, ln by 2, you can have this factor 0.693 by mu. Clear? This is a very important concept. This you have to do quick calculations that you will see very handy. For example, without, we will get to the details, but so I want to have only my small portion in my chest, I need to do X-ray, right. I do not want the X radiations to go to different part. What I can do? Oh, I can put a lead shield or whatever that will attenuate way more than your tissues. So whatever n I am sending, when it has to go through certain thickness of your lead, it will probably attenuate, and whatever after the attenuation comes in, going into the body will be very minimal. So you can design this thickness depending on the half value layer thickness characteristic of a material. You can say, oh, if you do not have lead, maybe you can use some other material, but the thickness of that should be more, right. So all this can be very handy in designing how much attenuation you want to control. Okay, good. So that is an important concept that you need to be very clear about, and I would not say memorize this, but if you recall this definition, you should know from the word half value layer thickness, you should be able to quickly relate this, and in that context it does not hurt to remember it as 0.693, but just do not remember the formula, Remember how you arrived at that. That is more important. Okay. So that is for your monoenergetic case. What we need to still do is kind of complete and say narrow beam monoenergetic photons. That is fine. So I am not changing the dimensions of my the beam or the detector, right, the narrow beam, or the energy. It is still only photons with one energy that is going in. One another variable that is there is my thickness, the slab. So that I varied, I got HVL. So only other thing is, why should I have only one slab? Can't I have two slabs next to each other? Can't I have more slabs next to each other? Each slab, right, has different material. So I can have one lead, I can have aluminum. So why should the path of the photons when it goes through the slab be only one mu or only one material? Can I update my equation, right? Can I update it when you have a non-homogeneous slab? So when I mean by non-homogeneous slab, the slab is one slab, you think about it, but then you have multiple slabs that are next to each other. So the path of the photon, it has to go through material 1, material 2, material 3 and so on and so forth, and then it exits. What we know, what we have derived so far is, when it goes through one material, we know how much is the reduction. Now we need to, when you have cascade, when you have several slabs next to each other, what is the output? A straightforward extension would be, what comes out of the first slab goes into the second slab, what comes out of second slab goes into the third slab, and so on and so forth. I know the attenuation, basic fundamental attenuation law, which is whatever goes in exponential of minus that material property mu, right, times the thickness of that material. That is the input to the next. So that is the output, but that output is the input to the next slab. The output of that slab is the input to the subsequent slab, and so on and so. So I can basically cascade this, right? I mean, to think about it. Okay. So that is a case we will now do, non-homogeneous. So we have d by dn is equal to mu of x. What is this mu of x? That means my attenuation is a function of where the length scale. So if you have multiple slabs, each slab has its own mu. That means along the x, mu is changing, right? So that is how it is denoted. Mu of x means which slab the x is corresponding to different slabs. As the x changes, you can have different slab, right? Different material property. So you are writing mu is a function of x. So I can have number of photons that are lost, right? dn by n is dependent on mu at each location, and therefore you can write at each x, that is whatever is coming at any given location, what is the number of photons? Oh, that is less than whatever number of photons you sent in, it is lost due to every length that is before that, right. So whatever you sent in, say let us say n0 is what is there without any material. So that is your estimate of your input, what you are sending out from the X-ray tube, that is your n0. At any location x, number of photons that are there is going to be whatever you sent in times exponential loss, right, when you arrived at that location. So 0 to until that x, whatever material that the photons have travelled through, it is a loss, each mu x dash dx dash, meaning each slab has its own attenuation. So x dash is one material at that location, right. So your mu is changing. So sum of all the losses until you arrive at x. So whatever you went in the input, right, it is getting lost depending on the material property and the length over which 0 to x of the material property, right. That is your n of x, straightforward. So you can write that as intensity also, which is I of x is nothing but I naught, whatever was sent in, and loss until before that. You can have multiple layers, multiple slabs, right. So you have mu x dashed dx dash. This is just a dummy variable along the length. Okay. So why is this important? Oh, it's an integral form of the fundamental attenuation law. What we saw already, right? Same thing is captured here. But then instead of just having one slab, writing one fundamental equation e power mu x or mu delta x, if you have non-homogeneous case, which is all interesting, right? Interesting is because eventually we are not interested in only one slab with one material, we are interested in biomedical imaging. So you are going to have different tissue materials, bone, soft tissue, fat, right? You are going to have several things, contrast agent, you can have several materials. So what you are sending in on one side of the body, what you are receiving on other side has to go through multiple different materials. That is why this is important, and therefore integral form, right, integral meaning it's this form that you are talking about, where you account for different materials, non-homogeneous slab is a very important part. In fact, whatever we have covered so far, this model, right, of what you send in and what you receive, and the model, this input output relationship using this exponential law, right, this is very handy even for PET. This is how we will we have to do our, see, this is physics, right. So we need to do our imaging, we need to talk about image as a model of model capturing the physics. Okay. So this form will be very handy, we will start to write this more often, not only here in projection radiography, but also in CT and also for PET. Okay. So let us quickly do one more, right. Linear attenuation coefficient depends on the medium property as well as incident photon. So this is the part that I kind of mentioned even when we talked about the different interactions, right, of your electromagnetic photon with your material interaction. What did we talk about? There is a energy range, at least for the signal part. Compton scattering, we didn't worry. We said for all the practical biomedical proper tissues, it is not energy dependent. But for signal we did talk about. Okay. So we did talk about that, and it turns out that this is how the plot is for your attenuation coefficient or your material property that we just talked about as a function of what energy you are dealing with. These are different material, bone, muscle, fat, right. This is the plot. In fact, we will stop here. It's a good point to stop here because we need to observe few things here and then proceed towards generalizing this a little bit more. What we covered is monoenergetic, that is fine, but then narrow beam, okay, we expanded it for non-homogeneous slab, but we need to talk about perhaps if it is not narrow beam, there could be wide beam, not one energy, multiple energy, not one slab, multiple slabs. All this we need to quickly generalize it further. So we will stop here. In the next lecture we will actually, it's a very nice material, it's all gradually building, very nice material. This is the heart of the physics that we need to understand before we jump into each modality and say, I know my signal model, I know my noise model, so let me write it out, and this is the image, is an estimate of your unknown underlying. So we can actually get there in a very, very interesting fashion. Okay. So we will stop here for the moment and see you in the subsequent concepts in the next lecture.